Hello again. This is part 4. There will be 5 parts. The next part, I'm going to redo what I'm doing now, just with pencil and paper and rulers, the old-fashioned way. Here, I think I can illustrate the principles of doing this with this computer screen. And then we'll move on to the next, doing it with just rulers on printed paper, pencil and paper. But so the idea is, if we have isobars like this, what wind speed should we expect here? There's nobody telling us that. And when you look at the maps, they also, a lot of the maps won't have it. These surface analysis maps, they have the winds from these various ship reports. 10 knot, nominally 10. Remember, that could be anywhere from 7.5 to 12.5, 20, 15, and so on. And so we can do this any place on the map, but just to illustrate the point, let's try one right here. This little circle, I've just cheated, and I'll show you what that's for in a minute. But so we want to know what the wind speed and direction is, say here or here, here, but I'm going to do it right here. Now, the way that you get the wind direction is always going to be going clockwise around the highs. So if you see, imagine here's a high. This wind is going clockwise. You see it around the high. Clockwise around the high. So these guys are kind of clockwise. They're going clockwise around the high. Now the equivalent way to think of that is counterclockwise around the low. So you see this wind here, which I could think of as going clockwise around this high over here, clockwise around this high. I can also think of going counterclockwise around this low. And the direction that it would be is not parallel to the isobars, but crossing the isobars. So the wind direction is crossing the isobars, and the rule is it's going generally into the low, and out of the high, into the low, and out of the high. Actually, when I look at this, into the low and out of the high, this guy's wind report, actually I didn't notice that, this guy's wind report's totally wrong, right? This is going into the high. So this is just a fortuitous situation where we learn something. This wind is not right. Here's a ship report. Now it's either just an error, I doubt that, maybe, but it could be he was sitting on a squall, but he says he was in fog. I don't know, but that wind direction is not right. If you look, here's a wind going that way, here's a wind going that way. This wind is flowing that direction in this area. That's interesting. Okay, see, it's going that way across the isobars, out of the high, yeah, except for this guy who just happens to be wrong, and into the low. So if you find any of these wind reports around, here's the low, they should be kind of going into it. All right, so you would have to be careful about that. The other thing is, how much does it cross the high? In other words, how much across the isobars? We use a general guideline that it's 2 points. Something like 2 points. That would be 22. In normal sort of calm conditions, 2 points, 22.5, 20, 30 degrees, something like that. 20. So this angle between the eyes, see, this is a little steeper, but let's come over here. See, this one's a little more gentle, but these are about, like, if you look at this is on the same map, but this is more gentle, this is more gentle than that, and this is a little steeper, except going the wrong way in this case. But here is about 22, 30 degrees. Here's a little stronger. So, but the rule is, that's the guideline. Out of the high, into the low, because the wind's going into the low and straight up. In the high, it's coming down from above and out. So it's into the low and out of the high. The other thing that affects that angle, and this is again discussed in our textbook, Modern Marine Weather. There's details about that. This angle really depends on the sea state. If the rougher sea state, it has a bigger angle. So the angle across the isobars is bigger, like you get strong winds or rough seas, the angle, the friction on the surface is higher, so that angle is a little steeper. When it's calm, it's more like the isobars, but still crossing. And you see that a little bit here. You see, if you imagine an isobar that's parallel to this one and parallel to this one, then right in here, you see this how gentle that angle is, and that's gentle, that's almost parallel, gentle crossing. But once you get up to where the wind's strong, 20, 30 knots, then the angles are a little steeper. So that's a guideline. Now, to figure the actual speeds, we're going to go back to our textbook. Let's see. Here's a section where we discuss why it behaves the way it does, but we end up with a formula. This is the formula when there's no friction, so it's 40 knots over, and this D, the way we've defined our formulas, we've balanced the reason that number is 40 instead of 12.8 or something or other is because we have defined our distance between the 4 millibar isobar spacing. This is the distance between 4 millibars isobars expressed in degrees of latitude. This is all to make it easy, and that's a sign of the latitude. But this is with no friction. When you start putting in the surface friction, then you see here we're recommending 0.8. You take that value, this is called the geostrophic wind, and we're taking that value and multiplying it times 0.8. That, if you surf around the textbooks and various nomograms and so forth, you will see that that actually is rather higher, a little bit higher than the normal recommendation, which could be as low as 0.6. Again, that number depends on the friction and the stability of the air. I mean, the roughness of the surface and stability of the air. But all in all, as an average for the ocean, we have found that 0.8 is a better value for doing this. You're not going to be right all the time, of course, because it's a lot of variables involved. So this formula then in this textbook, there's this table. And you can use this table without any computations. That's isobar spacing, the distance between 4 millibar isobars, expressed in degrees of latitude, and then this is the latitude. So let's do an example. Let's do an example of that, or a couple examples. So first of all, let me come up, let's see, plus. So what do we need? We need to know the latitude, and the latitude we're taking place. And this one, we can read this off of here. This is latitude 40. Okay, so down here it's 40, and this with tick marks. Again, over here you have no tick marks. So in the next plot, I'm going to show you how you divide that up into 10 divisions and stuff like that. But for now, we know that this is this is latitude like 48.5. So this is latitude 48.5. Then we need to know this distance expressed in degrees of latitude. So now I've got a computer and I can't show you my dividers, but the way you would do it on the boat with a printed chart is you put your dividers across here, measure that, put that distance on your dividers, rotate your dividers 90 degrees, and measure the distance off here. So I'm just going to do it this way. I kind of drew that circle, not kind of, I exactly drew that circle. Now I can put that circle on there to show you that that circle is about the distance between those two. And then I can bring that over here. Now this spacing is actually changing with latitude. Whoops, what am I doing here? It's changing with latitude. So you really, to do it right, you really want to do it kind of close to the point you're working with. What happened here? Maybe I better zoom out and get back on track. Okay, so here we go. Let me take that circle, bring it up here. That's a distance. And so we want to measure that distance, which I can do. I'll do it something like that. Okay, so there you go. So this is, what do we have here? These are tick marks, but look, if I zoom in on these tick marks, you've got 1 degree, then this is 1, 2, 3, 4, 5, 6. So these are 10 minutes. So this is 1 degree and 10, 20, 40. 1 degree, 40 minutes. That's 1.7 degrees. 1.7 degrees. So we have isobars that are separated by 1.7 degrees of latitude at 48.5 degrees of latitude. So let me get this. So I've got, what's my formula here? 40 divided by 1.7 equals, and then I divide that by the sine of, what do you say, 48.5. 48.5. Take the sine of that equals, and that's a 31, and then we take times a 0.8. 0.8 equals 25 knots. So we're predicting 25 knots. Now, they're reporting 20, but look, they didn't even get the direction right. So I don't know what's going on. They could have been in a squall, or there just could be some error there. That wind should all be from the southeast, really, there, not that direction. Sorry to stumble onto that at this point, but it's a good thing to keep in mind. It's just wrong. But that's 25. Now look, there's 20. They show 20, and this could go up to 22.5. So we're not exactly right on the money, but again, this is sort of, if we get within 10%, we're doing fine, by the way. 10%, and this stuff is fine. What is this line here? I don't need that line. Okay, let's just do one more that's up here, and I made a circle for this one. Let me bring it over and show that that's the distance up there. That's pretty close. Okay, so that's, well, let's come down. Anyway, you see if you, now again, the way you would do it, you'd put your dividers across here, then just rotate your dividers and read it here. It's actually, frankly, easier than what I'm doing with this thing here. And again, oh, now that's kind of a coincidence, but this also turns out to be, let's see, 1 degree and 10, 20, I guess 1 degree. That's again 1.7. But the latitude is now different, and that everything matters here. And this is at about 51.5, maybe a little higher, but let's just do 1.5 so I can get to an, well, let's see what it is. Oh no, yeah, that's about 1.5. All right, so back here, so what do we have? We have 40 divided by, again, it was coincidentally 1.7 equals, divided by 51.5. Take the sine of that equals. Now you can get all this out of the table. So here we're now low, divided by, and then we have times 0.8. So we're getting 24 here. So we get a little less, and we get in our formula here, we're getting a little bit less than what they're predicting. They're saying 30, we're at 24. But that's the ballpark you take. So we get this 30 could be as low as 27.5, and we're dealing with like 10% type of science here. So that's that. So the main point is you're up around 25. They say 30 here. It's an average. You can actually check this more precisely because you can digitally go online and see what that ship report really was. But I'll maybe look that up and report it later. But I wanted to do another one down here at a lower speed, and I did a circle on this guy. See here now, this is a little bit more of a challenge, both in direction and in speed. But let's just do the speed. And then here I'll come up plus, get it up where you can see it. Bring my dividers, so-called dividers, over here. And I want to get, actually, might want to go just down a little bit. I wanted that to be right about the middle of the circle. Well, again, if I had, I'm going to do this with the paper and dividers, but I have to do a different kind of video. So what is that kind of spacing? That looks like it's about 1, 2, 3, 4, 5, 6 degrees. So this spacing of the isobar is at 6 degrees, and this guy's, let's see, what's his latitude here? That's 30. So he's at what? This guy's at like 29.5. All right. So now, again, we can look in the table, but I just do it this way here. 40 divided by, what was our spacing? 6 degrees equals 6 point that. Then divided by 20, what do we say, 29.5. Take the sine of that equals, again, no, and then that's 13, but that's no friction. Then we go to times 0.8. 0.8 equals, and we're getting 10 knots, 10.8. So now you see there's the difference. This kind of spacing at this latitude is 10 knots. And that's well, 11, but this could be anywhere from 7.5 to 12.5. So that kind of agrees. But look, just right up here is, they say 20, nominally 20. But I'm not going to do this one, but you could do, well, no, you can't do it. I don't know. But if you do this, you can practice this. But if you look here, see that spacing is, doesn't, a quick glance doesn't show it, but that's a huge difference in the spacing. Plus, it's a higher latitude, a little bit higher. So that's the way that works. And again, the next video I want to do it, show you doing it on a paper with a projected. Now, projected video. If you want to get this direction here, now how are you going to get that direction? The way that, let's see if I can actually draw here. So what you would kind of do is just do the best you can to draw an well, that's not very, oh, wow, what a fancy program. That's pretty good. Gosh, I didn't know it did that. So I've drawn kind of like a parallel isobar here. And it's not that parallel anymore, but it's something like that. And you see, what I want is that going about, oh, that's even good. That's like 22, 2 points, 22, 25 degrees into, actually, though, it's going into the high. Yeah. Things must be changing here. This, in principle, should be going not... What am I doing wrong? I'm not doing anything wrong here. I'm not in the wrong hemisphere. No, these just aren't... These winds... This wind could... In other words, if you had to guess which way this wind is going, you wouldn't guess the direction that this fellow reported. You would actually guess that this was a little more pointed out this way. Little more, you see, if there's a high and I'm going out of the high, that line should go, more like this direction here, which I can draw when I get a real pencil. Really should be a little more westerly. Now, so here now a little subtlety on map reading. Look at this. All these ship reports. My conclusion from this is, look at this guy and this guy both going, I think their isobars are probably not right down here. Simple as that. Let's say the ship reports are right. The one upstairs we saw, that's just wrong. But this one, here's the question is probably the isobars are not right. These isobars are not right. They probably come come out of the high. Well, I have to draw a picture to figure that out, but they're not consistent. So I'm going to let that go, and then I'll think on that between the two videos, and then address it when I come back, and maybe make a sketch to what I think they'd be based on that observation. And I'll stop there on this one. Again, you can do it all with the tables without any computation that's in the textbook.